the second part of the gravity chapter. And here we are talking about, like, summarizing the relations that we are talking about. This is how you are going to calculate G. And as I said, this is for any planet. And that value can be used to find out what is the mass of the Earth. I will say this formula, this equation is very powerful, and this is the one that enabled us from. This is one of the equations that enabled us from measuring the masses of, like, the Earth, the Sun, all the stuff. In 1798, we already had measured G and calculated the radius of the Earth. We just needed to find the universal gravitational constant. And there is a scientist, his name Henry Cavendish. He was the one who performed an experiment to calculate what is the value of that G, where he have like two masses, and he was using light to measure the deflection of the laser beam, and from that he was able to find some of the measurements to calculate G. With a value for G, we found the mass of the Earth, and it was calculated as 5.97 10 to 24, or like about 6 10 to 24 kilograms. We're gonna try to do the same with Io, which is one of the moons of Jupiter. Several volcanoes have been observed erupting on the surface of Jupiter's closest Galilean moon, Io. Suppose that material ejected from one of these volcanoes reaches a height of 5 kilometers after being projected straight upward with an initial speed of 134 meters per second. Given that the radius of Io is 1820 kilometers, calculate the mass of Io. First, I need to find what is the value of G, and I did use here conservation of energy. I considered this point here on the surface to be my I, and my UG equals 0, and then here K maximum is 0. Then I said 1/2 mv squared equals mgh, and then from that G was calculated to be 1.8 meters per second. In addition, we know that mg equals the weight of the object equals the force of gravity, which is gmm over r squared. Then from that I can cancel the mass of the object, and from that I will be able to calculate the mass of Io to be 8.99 10 to 22 kilograms. Now, I will say, and we, like always, we know that Newton was not the first one to talk about gravity, or to discuss the let's say these forces in the universe. Like Galileo, of course, we know that he was talking first about gravity, but also there is a scientist, he was a mathematician, his name Johannes Kepler, made detailed studies of the apparent motions of the planet over many years. I believe maybe they were 30 or 40 years. And he was able to formulate 3 empirical laws. Empirical means he did not provide any proof for these. He did not. And Newton after that was able to verify these. The first one is planets follow elliptical orbits with the sun at one focus of the ellipse. Now the ellipse is different from the circle, that it has it doesn't have a fixed radius. then the distance it is like oval shape, or it is, we call it elliptical. It has two foci, and the sun is sitting at one of these foci. Now, if we will find the center of that ellipse, then that A here, we call it the semi-major axis. And here C, it is the semi-minor axis. There is a number that is measuring for us how elliptical is the shape. We call it eccentricity, and that E is C over A. I will say most of the planet, the orbits are not really very, very elliptical. They are deviating from being a circle, but the most elliptical is Mercury. Now, the second law is talking about, we call it equal areas in equal times. As a planet is moving in its orbit, it's sweeping out an equal amount in area in an equal amount of time. Then if it's gonna go from A to B here in 1 month, and from C to D in 1 month, and then if we will calculate the area here, it should equal the area here. Now, this law has been very beneficial to us, and it gave us, like, of course, like if we're gonna assume that we have circles, then the object is gonna move in uniform circular motion. Then its speed is gonna be constant throughout the motion. What's going on here is that the speed is changing, and the object is gonna move faster when it is closer to the sun than when it is far. The third law, it is connecting T, capital T, which is, we call it the period of the motion, which is the time needed for one cycle. It is connecting it with the average distance to the sun, and it said T equals a constant R to the power of 3 over 2. This can be shown to be a consequence of the inverse square law of the gravitational force, and it can be used in this simple way. T1 over T2 all squared should equal R1 over R2 all cubed. And here, this is T can be measured in years, and R can be measured in AU. We don't have to convert here since the units are going to cancel. This is just showing you the derivation and what is the value of this constant. We can say that sigma F equals MA, and then Fg equals m times the centripetal acceleration, which is v squared over r. And then here we're gonna put gmm over r squared, and then finally we can say that t squared equals 4 pi squared over gm times r cubed. This is the one that has the value of the constant, and this is another way that we now use to calculate the mass of planets or asteroids, like in this one. An asteroid with its own moon, the asteroid 243 Ida has its own small moon, Dactyl. Given that the orbital radius of Dactyl is 89 kilometers and its period is 19 hours, calculate the mass of the 243 Ida. The radius, we need to have it in meters, and the period also should be in seconds. And then t squared equals 4 pi squared over gm r cubed, and then m is going to be 4 pi squared r squared over t squared over g, and with all these values plugged in, you're gonna find 8.9, 10 to 16. Now, how do we keep a satellite up? We have, like, this is like was predicted by Newton. And let me see if my link here is gonna work. Like, you can, like, this is very interesting. You have here so many things that we can look at if you are interested. The one that I'm looking for, it is about, okay, let me like explain to you. Like, I can't find it here. I don't know why I lost it. I used to have it also in Java, but now Java is not working. Okay, let me then explain this to you. I lost the. Let me see again. It's gonna. Okay. Okay, this is, as I said, the geocentric thing. Okay, let me explain this to you. This is all about the geo satellites here, and you can look it. I like it. Like, I'm just gonna spend the whole time just looking at it, but just let me go back to here and talk a little bit about what's going on with Newton's orbital canon. We let's assume here. Okay, what's wrong with my pen? If we have the Earth here, okay, and then we, like in Newton suggested, we're gonna go on top of a mountain, and then we are going to fire something horizontally. Then for a certain speed, it might hit here. If we increase the speed, it might hit here. If we keep on increasing, we're gonna find that the satellite is gonna go in a circle. This is about the speed, like 8,000 meters per second. Now, any speed above that, this velocity is gonna make it go into elliptical orbits. Then this one is going to be circular. And this is usually what we do with orbits, with satellites. Okay, then we're going to go to an elevation, and then we are going to send it with that velocity, and then it's going to stay in its orbit. Okay. Astronauts in the space shuttle float because they are not so far from the Earth. Thus, Earth's gravity doesn't act anymore. A gravity force pulling them inward is cancelled, while gravity is trying to pull them inward. They are trying to continue in a straight line path. Now, this is the reason because astronauts in the space shuttle float because they are in free fall around the Earth, just like a satellite or the moon. Again, it's gravity that provides the centripetal force that keeps them in circular motion. Now, Kepler's laws of orbital motion, how do we keep the satellite up? We know that this is the equation that we are using for calculation of V. Then I will say V squared is going to be G m of the Earth divided by R. Then if I want to send a satellite in an orbit R, I should have that velocity satisfying this formula. Now, I will say here, again, geosynchronous satellite is one whose orbital period is equal to 1 day, which is like synchronized with the rotation of the Earth. If such a satellite is orbiting above the equator, it will be in a fixed position with respect to the ground. Are used for communications and weather forecasting. Okay, then we can calculate the value of that radius for that velocity to be from the center of the Earth to be 36,000 kilometers above the surface. Now, also here, we need to know that also it's the same idea about GPS satellites. We have them sent in like orbits. GPS satellites are not in geosynchronous orbits. Their orbit period is 12 hours. And, I'm not sure about their number. I'm not sure about their number. I used to know that, but I think maybe they are 12, 11. I'm not sure. And we use like more than one satellite to measure the distances precisely on the location of the Earth. Okay, the moon does not crash into the Earth, and this is maybe some of the things that we need to know that because it is in the Earth gravitational field, and it's gonna keep it in that orbit. This force is enough to keep it at this radius because it's high speed. If it is stopped moving, it would of course fall in directly into the Earth. With its high speed, the moon would fly off into space if it weren't for gravity providing a centripetal force. Here we will say Fg equals mv squared over r. Now, when we are, like very far from the Earth, the gravitational potential energy of a function is not going to be mgh. It's going to be modified to be minus g m mass of the Earth divided by r. very close to the Earth is going to be modified to this quantity, and this is really G is going to be if you will take R equals H at the surface of the Earth is going to give you G. Gravitational potential energy is just like all other forms of energy. It is a scalar, therefore has no component. It is just a sign because that energy is going to make objects bound to the Earth. Here we are trying to calculate, using that in calculation, calculate the gravitational potential energy of a 8.8 kilogram mass on the surface of the Earth, and then at an altitude of 350 kilometers. Take the difference between the results for parts A and B and compare them with MGH. Okay, I did this here. I have calculated U for that altitude, and then 10 to 8 joule, and I have calculated at the surface of the Earth, and then I took the difference between them, and I have calculated here MGH 310 to the 7. It's approximately the same value, and it is just the difference between the two values. Now, when we're going to talk about energy conservation here, total mechanical energy is going to be the kinetic plus the gravitational potential, and is going to take this form. This confirms what we already know, that the object, it moves faster and faster as it is approaching the Earth. Okay, then here, this is the U. We have it like E versus R, and you can see that the U value is really increasing, the U here, and the K also is gonna be more like increasing. This is another way of visualizing, like from quantum physics, the gravitational potential well, as if it is like something that is gonna bring objects and attract. Now also, when we are really increasing the speed, remember when I was talking about sending an object with a horizontal velocity, the escape velocity, we are getting the initial upward speed a projectile can have in order to escape from the Earth's gravity. And this is 11.2 kilometers per second, or 11,200 meters per second. This is here speed of a projectile as it leaves the Earth for various launch speeds. And finally, the black holes, they are really very massive, sufficiently small, and the escape speed will equal or exceed the speed of light, and this is the reason why even the light will not escape. And light will be bent by any gravitational field. This can be seen when we view a distant galaxy beyond a closer galaxy. Cluster. This is called gravitational lensing, and many examples have been found. Here just to show you how we are calculating the escape velocity and how it is affected by the mass and the radius. Suppose a planet is discovered orbiting a distant star. If the mass of the planet is 10 times the mass of the Earth and its radius is 1/10 of the Earth's radius, how does the escape speed of this planet compare with that of the Earth? Okay, I have that is the one for the Earth, and for the planet I have it here. And then after I rearrange, I get my constants like 100 for like VP squared. It is 100 times V escape of on the Earth. And that is when I take my square root, is going to be 10 times the escape velocity of the Earth, which means it is 112 kilometers per second. And this is making sense since the mass is greater and the radius is much less. Tides, usually we can treat planets, moons, and stars as though they were point objects, but in fact they are not. When we have two objects that they are really having, let's say, huge masses, they exert gravitational force on each other. The force on the near side is larger than the force on the far side, okay, because of the difference in distance. This difference in gravitational force across an object is called tidal forces. And the tidal forces is gonna here create general tidal force on the left and the result of lunar tidal forces on the Earth on the right. And this is gonna make it result in orbital lock-in, where the moon always has the same face toward the planet as does the Earth moon. Okay? If the moon gets too close to a large planet, the tidal forces can be strong enough to tear the moon apart. This occurs inside the Ricci limit of the black holes. And this is the summary of the chapter.